So I'm going to tell you a bit more about the geometry of loop quantum gravity, building on what Simone Speziale told you about before lunch, if you didn't forget everything during lunch. So I will start by telling you my visions of quantum gravity. Then I will present what's loop quantum gravity. I will tell you about entropy in loop quantum gravity and about correlations on these p-network states that we use in loop quantum gravity. So first, quantum gravity. What am I going to talk about? So the goal of loop quantum gravity, of quantum gravity in general, is to find a new type of geometry, a new concept of geometry to replace the paradigm of continuous or differentiable manifolds. And this new concept of geometry is supposed to be to unify our vision of gravity through general relativity and quantum mechanics and quantum field theory. So in order to solve all the problems of these theories, so get a general relativity without singularities, with finite quantum fluctuations of the geometry, and a framework of geometry which naturally encompass some property of quantum mechanics or like some quantum space-time features. So a bit more precisely, gravity, it's about, is described by general relativity, so it tells you that all of gravity is contained in the geometry. So space-time is curved, and the matter is a source of curvature. So since matter is going to be quantized, space-time is going to be quantized too. So we expect to have quantum states of a geometry where all the geometric observables such as length, areas, volume are going to become quantum operators. And so we're going to have some quantum fuzziness of a metric of the structure of space-time. And another key feature of quantum theory, it's the concept of path integral, meaning that between some initial state and some final state, we have a superposition of all possible trajectories, of all possible paths. And so here, between our initial state of geometry and our final state of geometry, we're going to have a superposition of all possible space-time geometries, and that's going to be our quantum space-time. So the main tagline to remember is that in quantum gravity, we don't have any fixed background space-time. The geometry is completely dynamical, and it's going to be quantum also. So I'm going to refine things slowly and get more and more complicated. So there's two main ways to see general relativity of the evolution of geometry. So there's the canonical formulation, basically, which relies on the splitting of space-time, of a four-dimensional space-time, into three-dimensional space, which are going to evolve in time. So classically, you're going to have a 3D metric, and you're going to see it evolving in time, and its evolution is going to make your 4D space-time. So now, when you make that quantum, you're going to have wave function of your 3D metric, and you're going to have equations of motions, what we call the Hamiltonian constraints, which must be satisfied by your states. And these are going to be the equivalent of the Einstein equation for general relativity at the quantum level. Then there's the Covariant Framework, where you try to quantize the path integral for general relativity, meaning that you consider some region of space-time, and you're going to sum over all possible four metrics in there of the exponential of, I forgot an I there. There must be an I in front of the action of general relativity, which depends on my four metric. And so the correspondence between these two points of view, which is more a space plus time point of view and a space-time point of view, is that the canonical framework is going to define the boundary states that I put for my path integral, so the initial and final states. And this path integral is going to tell you the transition amplitude between the initial and the final state. So these are two complementary visions of the theory. So now, stated like that, it seems it's a straightforward thing to take general relativity and quantize it. So why is it hard? What's the problem? It turns out that the key feature that we've identified in general relativity means its symmetry, which is invariant under the diffeomorphism, is actually the reason for it to be complicated. So what is this invariance of the diffeomorphism that quantum gravity people keep talking about. It comes straight from the relativity principle, meaning that physics is invariant of the change of observers. Okay, we all observe different things. We're going to measure different speeds and all that, but we know how to define a coordinate, a change of coordinates between my reference frame and the reference frame of somebody else. And so my measures can be mapped onto the measures that somebody else will do of the same physical reality. So when you write when you implement that into general relativity, it's going to be formalized mathematically as the geometry being invariant to the diffeomorphisms. So basically, like somebody tells you, uses a coordinate system and tells you that's my form metric that I see. The world is like that. Somebody else is going to be in a different motion and is going to see a different metric. And the metrics seen by these two observers is going to be related by a diffeomorphism. So they describe exactly the same physical reality. And then at the quantum level, this symmetry, the concept of symmetry is fundamental. And so this invariance of the diffeomorphisms is just going to be identified as a gauge invariance of general relativity. So something which is, means that two states which are related by a diffeomorphism must be the same state. And that's what makes quantum gravity complicated. So why does it make things complicated? Is that now the diffeomorphism, they move points around in your manifold. So like diffeomorphisms, like, well, I don't know how to, I don't have any picture, but basically you can move things around. So if you can move things around, systems around, points around, and it's still the same state, how can you locate points? So for example, the most stupid question, where are the quantum gravity degrees of freedom? If geometry can be moved around, where do I say, oh, this is a local degree of freedom, I can fluctuate this? So the main idea is, actually the most simplest idea is that if we can't locate one system, we can still measure how systems interact. So like the most reasonable proposal is to use relational observables. So you can see how systems interact, and so you can look at correlations between systems, and you can try to rebuild the distance and a metric, an effective metric from the correlation that you measure. So for example, if you look at the two-point function in our theory, so here I wrote a field phi, but you can take the metric or any degree of freedom of general relativity, and you expect it to go as the distance square, at least around the flat space-time. So you can, if you don't know the distance, but you know the correlation, you can always try to reconstruct it from the correlation. In some sense, it's saying, okay, the gravitational force between 2 points, I know it's 1 over the distance square. So it means that if I know how two things attract each other, I can deduce the distance between them. And it's how actually we measure the distances between astrophysical celestial bodies and so on, by the effect of gravity. So that's the first idea. The second idea is that if you want to stop things from moving around, you just put walls. So you put boundaries so that things can bump into there, and somehow you locate things by putting boundaries. And this idea of boundary is similar to the idea of what happens with the path integral. So somehow, when in the path integral, once you put the initial and final state, and inside, in the middle, it's a superposition of every 4D space-time that can happen. But somehow, your initial and final state are supposed to put strong enough constraint to tell you if there's a semi-classical space-time in between, and what's the structure of space-time that interpolates between these two states. And here, when I talk about boundaries, I'm not talking only about space-like boundaries, but it can be time-like boundaries, any type of boundaries. So when you put these two ideas together, what comes out of it is that the degrees of freedom of general relativity, of quantum gravity, are going to be non-local degrees of freedom, meaning that it's not going to be local in one point. You're going to start looking at correlations, and that's going to be your degrees of freedom. And the idea of holography. So usually when people hear about holography in quantum gravity, they think directly, oh, it's black hole entropy. It's that the entropy of the space-time of the space region is proportional to its area and not its volume. But actually, holography, it's a bit deeper than that. It means that if you start on the boundary data is going to tell you the structure of a bulk data. So you have, like, imagine you have a region of space-time, of space, and I know the geometry data around my sphere, or my region, on the boundary, and it's going to tell you how the geometry is inside. And the way it's done, it's basically, if you want to locate a point inside, you look at points of correlation between points on the boundary, but it cannot be like very close points. If you want to have an idea of depth, you have to look at non-local correlation on the boundary to probe deeper and deeper inside the bulk. So that's the general ideas about quantum gravity. So now I'm going to tell you about the mathematical framework of loop quantum gravity. So kind of revising what Simone just told you before lunch. So the basics of loop quantum gravity is that first, we don't use the metric anymore. We replace the metric by a pair of variables, which we call the Livine or the tetrad, and a connection. So the tetrad, it's a basis on the tangent space of your manifold. Basically, it's a local coordinate system. Then the connection tells you how the coordinate system changes when you move from one point to another one on the manifold. The second point of loop quantum gravity is that it's a canonical framework. So you do a 3+1 splitting of space-time, and so you're going to describe the geometry, the three-dimensional geometry of space, and how it evolves in time. Then the third step is that you have these continuous fields. You're going to discretize them to identify suitable observables, which Simone described you as holonomy observables this morning. And you're going to quantize them by using some wave functions of the geometry. So this theory was introduced by Abhay Ashtekar, Carlo Rovelli, and Liz Morlin. So I'm going to skip the whole quantization thing and just tell you the result right at the end. So what happens is that instead of having some continuous 3D manifold, we're going to work on a graph, which we can think as to be embedded in some three-dimensional space, but not necessarily the three-dimensional flat space, a three-dimensional space. So you have a graph. So you have nodes and you have links between the nodes. And you're going to put variables on this graph. So on the links, you're going to put some group elements of SU2. And at the nodes, at the two ends of the node, you're going to put two vectors, three-dimensional vectors, which you can identify as Lie algebra element in SU2. So if you take one edge, you've got one group element and two vectors. If you look around the node, you have many edges, and you're going to have one vector for each edge that pokes from the node. So the phase space that you have, your symplectic space, is going to be T star of SU2 on each edge. So basically, your group element is your coordinate, and then the x's, the vectors, have a derivation on your Lie group. So in some sense, you have this network of relation. You have at every point some vectors, which describes all the direction that you can probe from this node. And then your degrees of freedom have these group elements in SU2, which tells you how you change the coordinate system in one point to the coordinate system at another point. Because you can think of SU2 as a representation, as defining some three-dimensional rotation from one point to another one. So of course we put some little constraints on these variables. It's not as simple as just as this. So you're going to put some constraint on each edge, but very natural, saying that the vector at the end of that edge is simply the image of this vector by this rotation. And you're going to add another constraint, which we call a closure constraint, meaning that the sum of the vectors at every node sums to 0. And so then the quantization goes as so, is that we're going to take wave functions of these group elements. Then the closure constraint here actually generates an invariance under SU2 at every node. So we use wave functions which are invariant under rotation at every node. And we find a nice basis of such states, which we call the spin network basis. So the way it's done, it's using the Peter-Weyl theorem that Simone breezed through this morning, which is a kind of Fourier transform of SU2. And so what you're going to get is that on each edge, you're going to have a spin, which is a representation of SU2, which is a half integer. So a spin, as I said, is an irreducible representation of the SU2 Lie group. So it's labeled by the spin, and the Hilbert space of that representation, I call it Vj, and it's of dimension 2j plus 1, and the basis has 2j plus 1 states, Jm, which you can think of, you should think of as polynomials of two variables homogeneous of degree 2j. And then at every node, you put an intertwiner. So an intertwiner, it's an SU2 invariant state. So if you look at a node and that has n edges linked to it, each edge carries a representation, a spin. And so you can consider around this node the tensor product of all these representations, and then an intertwiner is simply an SU2 invariant state in the tensor product of these representations. So now, what's the nice features about these spin network states? Is that they diagonalize all the geometric observables, so areas and volumes. So the idea, the kind of picture you get is that if you look at the area of a surface that is transversal to an edge, and that edge carries a spin j, then the area of that surface is going to be j in Planck area unit. And then the volume operator is going to act at every node of your vertex, and it's going to depend on the intertwiner that lives at that node. So in some sense, you got an idea of a discrete geometry, which is defined by this spin network. So to be more precise, it's exactly what Simone explained this morning. Around each node, you have all your free vectors, and you can, there's this Minkowski theorem that tells you that you can identify all of these vectors as the normal vectors to the faces of a convex polyhedron. So you've got n vectors, which sum to 0. There exists a unique convex polyhedron such that the area of each of its face is the norm of these vectors, and the direction is normal to these vectors. And then, so that's around each node, so you've got this polyhedron, and then along each edge, we know that the normal vector to that face was a rotation of the normal vector to the other face. So they have the same norm, so they have the same area, these two faces, but there's a problem that they not necessarily have the same shape. So you kind of glue polyhedrons like that, which do not have a shape matching. And so we call that twisted geometries. And that's actually the concept of discrete geometry that Simone introduced. It's his name. So now that I have spin networks, I know that they are discrete geometries. What am I going to do with them? So coming back to the start, it's that there was no a priori geometry, no background geometry. The spin network is not embedded into one 3D space. It defines the 3D space. It's going to define the 3D space into which you're going to embed the graph. So it defines the geometry by itself, and there's no background metric. And then these spin networks, this is space, they're going to evolve and they're going to fluctuate. So if the graph and the data on it can fluctuate, the geometry is going to fluctuate too. So one way to imagine a bit what's happening is to go to what is called graphite models. It's reducing the spin network dynamics to simply fluctuating graphs. So instead of putting spins, which are half integers, you just put that spin 0, that there's no edge, or spin 1, but there's an edge. So simply these spin networks reduce to some adjacency matrix between vertices. And then you can put some dynamics of creating and annihilating these edges. So typically the kind of dynamics you put is that if there's 3 points, 3 nodes which are related by 2 edges, you create another one. And if there's 3 points that are related by 3 edges, you can remove one of them at random. And actually this kind of of dynamics is simple enough to describe the formation of dense regions of spin networks, which are high mean connectivity, and so on and so on. But I must say that they have not been studied so much as they should or they could. But it gives you a good notion of what you mean by a fluctuating locality, meaning that the graph defines what's local. So 2 points are going to be close by or going if they are related by a few number of links, and so on. And you're going to define dense regions by high connectivity and low density regions by low mean connectivity of the nodes. And it's the same kind of thing that we'd like to do for spin networks in general. So we have this picture of discrete geometries with like these local polyhedras, but it doesn't give us really a notion of large-scale geometry. And since we want to talk about geometry, we'd like to be able to reconstruct a 3D metric, even a semi-classical 3D metric. We need to understand like distances and so on. And so the main way we can envision to do that is to look at correlations between the degrees of freedom living on the spin networks. So correlation between the spins and between the intertwiners living on that graph. And beyond that, we hope to be able to use such a construction to identify a good notion of observers, what we mean by a quantum coordinate system, and there's lots of problems to solve, like really how to implement and solve the Hamiltonian constraints, so the quantum Einstein equation, understand changes of graphs as changing of DFOs, so coordinate change, the cross-graining of these states to get the continuum limit and recover general relativity from low quantum gravity, define boundaries, describe evolution, plenty of things. Which are not done entirely yet, but it's all work under progress. But before going into correlations, I will tell you a few words on the evolution of spin networks. So, like if you want to describe the evolution of a spin network, it's what we call spin forms which are histories of spin networks. So basically, if you have a spin network, which is a graph, at each node you put some intertwiners, and at each edge you put some spin. So now you're going to make them evolve in time. So the nodes are going to become edges, and the edges are going to become faces. So now on the spin form, a face is going to carry a spin, and the edges are going to carry some intertwiners. And then at some point, these edges, these spin form edges, they're going to meet each other. And they're going to meet each other at points in space-time. So I will just call them spin form vertex, where these edges meet. And at these edges, when these edges meet at the spin form vertices, it means there's something happening. It's the points where the graph changes. And so it's at this point we're going to attribute a transition amplitude, which is going to describe the probability that an initial state will be turned into a certain final state. So all this can be formalized as dual to 3D triangulation evolving into 4D triangulation. So I'm not going to describe that into details, but basically, like if you take a 3D triangulations with tetrahedron, you can see it if you associate to each tetrahedron a point, and to the triangles between two tetrahedrons and edge, from any triangulation you can map it into a 4-valent graph. And the areas of these triangles are going to become the spin on the edges. So a 3D triangulation can be seen as dual to a spin network, and then you can make this spin network evolve into spin forms, and it's going to be equivalent to seeing this 3D triangulation evolving into 4D triangulations. So somehow, the main point I want to say here is that the spin form vertex are going to be dual to 4D-dimensional cells, which basically tells you that these are the basic structures of space-time, which we can call the space-time events, where something happens. And then once everything is formalized in terms of 4-dimensional triangulations, or in general 4-dimensional cellular complexes, it turns out that you can reformulate all spin form models as topological quantum field theory models, state sum models. This is the techniques that's used. And somehow the spin form give you the 2D and 3-dimensional and 4-dimensional structures, so spins, intertwiners, and a partition function. And what's missing, obviously, to have a full description of a four-dimensional manifold, it's one-dimensional objects and the zero-dimensional objects. And actually, identifying the algebraic structure that you identify to one-dimensional objects, this is particles word lines, and to zero-dimensional objects, which are actual particles meeting at a point, so scattering, is the main problem for people looking at the mathematics of extended topological quantum field theory. So this is an active area of research which is interesting both for quantum gravity but also in mathematics for people who like category theory and so on. So I'm going to put all of this topological quantum field theory aside and come back to simpler stuff and talk about entropy on spin network state in loop quantum gravity. So the setting is very simple. I have a spin network, some graph, and I'm going to look at a region of that spin network. So I take a set of nodes, I put a little surface around it, and if you look at the boundary, at the surface boundary, of the boundary surface, I mean, it's punctured by some edges which carry some spins. So now that my boundary surface is going to be made by some area patches which are dual to these edges, which carry some spins, J1 to Jn, and the total area of my surface is just going to be the sum of those spins. And my boundary state is going to be living in the tensor product of the representations corresponding to those spins. So I'm going to study that. So I'm going to simplify all that by removing all the structure inside the bulk and reduce it to a single point to start being able to do something explicit. So when I do that, it's that I'm thinking of a single intertwiner. So you can think of studying what happens with a single intertwiner as some prototype calculation for a black hole, but very prototype, very simplified, but it already starts to give a flavor of black holes. So what I'm going to do is look at all intertwiners for a fixed boundary area, so fixed J, big J, which is the sum of the spins. So it turns out I'm looking at the invariant, the space of SU2 invariant states in that tensor product, and I'm summing over all possible combination of those spins that sum to this big J. And I call this Hilbert space R, J, N. And we can prove that it carries an irreducible representation of a unitary group of N objects. You can find out, you can compute the Casimir, and so you can deduce from that the highest weight and the dimension, and it turns out that it's given by this Hooke formula in terms of binomial coefficients. So where does this action of a unitary group come from? So to do that, we need to deconstruct a bit what we did. So if we start with a phase space, which is C. When you quantize this phase space, it's just a harmonic oscillator. Z, like my complex variable in C, is going to be quantized as the annihilation operator A, and Z bar is going to be quantized as the creation operator A dagger. And the basis of states is going to be the basis of a harmonic oscillator, so just labeled by integers. Now, if I take C squared, it's going to be a pair of harmonic oscillators, but you can actually map that onto all SU2 spins. So simply, there's a change of basis between the two energy levels and a spin system. So the sum of these energies of these two harmonic oscillators is going to be the spin, and the difference between them is going to be the magnetic momentum. And that's simply Schwinger representation for SU2 representations. And then what we do when we look at our boundary with n spins is that we look at C2n, so n copies of C2, and you quotient it by SU2. So you look at SU2 invariant state. Actually, I've put 2 bars because it's the symplectic quotient. So it means that I am imposing the closure constraint, meaning that the sum of the x's sum to 0, so that it's going to be dual to a convex polyhedra. And I'm looking at the equivalence classes of this polyhedron under 3D rotation. And so when you quantize this space, it gives you this space of all possible quantum polyhedras. And so if you look at this phase space, there's a natural action of un on C2n. Simply, you've got n objects which are complex. I can act with a unitary group on that. And that's a very nice action, actually. So first, well, here it's a mapping between the complex variables and the vectors using the Pauli matrices. And once you've assumed that definition, then you find out that this unitary group action on my complex variables, C2n, is going to commute with my closure constraints. So it's going to map a polyhedron onto another polyhedron. And it's going to leave my total area boundary area invariant. And so actually, it's an action of the unitary group on classical convex polyhedras with n faces, which is going to change polyhedras into other polyhedras. So it's kind of fun because these polyhedras don't always have the same shape. So it can map some cube onto some double pyramid and so on. It can do some more complicated things. And actually, you can show that it's a cyclic action. So it maps all polyhedras onto all possible polyhedras. So you can start actually with a totally squashed polyhedron. So something like that. It's in crepe. And then you act with a unitary group and you build up some volume inside. And then there's some fun stuff, like if you look at concentration of measure on UN, it's going to tell you that for n very large, the most probable shape, like all possible shapes at random, is going to be very close to a sphere. So once we've digested this intuition, this geometrical intuition, we can come back to the dimension of my intertwiner space. And then you just say, oh, okay, these are all the possible states at my node. These are the number of intertwiner. It can compute the number of degrees of freedom of that and get an entropy. So I compute the log of this number for very large area and number of edges. So the natural question coming from gravity is like, do we get an entropy area law? This entropy scales like the boundary area. But here we've got two numbers. We've got the boundary area and we've got n. So what should we do with n? It turns out that, well, we can try to keep two numbers like that, but in that case, there's no real regime into which you naturally get the area law. So you think, okay, maybe I'm going to sum over all possible of punctures, all possible of edges around my area patches on my boundary. But then this number can go from 0 to infinity and totally diverge. Actually, we identified the problem is that if you have a finite area, I mean, obviously you think that you cannot have an infinite number of area patches since you've got a lowest area for these patches. But we've allowed for the spin 0. So we allowed for lots of patches to have a 0 area, which is pretty dumb. So the main problem is going to be to remove all the spin zeros and to start with the lowest spin, which is 1/2. In that case, we can have only a finite number of area patches on the boundary, which is bounded by 2j, and then we can sum over all these numbers and get some finite answer. So to do that, you can do a binomial transform on my dimensions of my number of intertwiners and get a number of intertwiners without spin 0. Then you can sum over them. And then you get that you get an entropy which only depends on the area, which scales like the area. So if you think about what we've done in terms of intertwiner, it's not very surprising. You put spins and you get something that scales as the spins. But if you think about it like in terms of the geometrical interpretation, like at fixed area, you've summed over all possible volume shapes. And so it's, in that case, it's surprising that you get an area, an entropy that scales like the area, like the boundary area, and not like the volume. So that's to say that this result is cool. Okay. So let's go a bit further into the entropy and see what more we can get from this very simple intertwiner model. So it was already simple. We can simplify it even more to get a super simplified model of a black hole. So we can set all the spins to the lowest value, 1/2. So why would I do that? Besides the point that it's simple, it means that you're taking the smallest area everywhere, so you have the impression to do it something more fundamental, like like probe the surface with the highest resolution with little areas which are all at the Planck scale. It also mathematically, you can think that it avoids overcounting because any spin is a tensor product of spin 1/2. So if I've got some spins, I can decompose it into tiny and tiny bits which all carry a spin 1/2. And somehow it models what like an old idea by Wheeler and plenty of other people about some horizon with qubits on it. And mathematically, it also makes things very simple because the area is simply proportional to the number of area patches. So J is simply n over 2. So it makes the mathematics very simple, and we can compute the dimension of the intertwiner space between two n spins 1/2. So remember that a spin 1/2 is simply a qubit, so it's a two-level system. It has the state up and state down. So I look at the intertwiner space between these guys. Somehow this has an interpretation in terms of quantum communication protocols. So imagine that I'm sending qubits to somebody, and that somehow I forgot to tell him what was the direction, my reference frame with which I send them. Meaning that he doesn't know in which direction to measure these qubits. In that case, he can measure the qubits with any direction he wants, but the only information that he will be able to get will be in the invariant subspace. So the other person will not be able to read any information which was not invariant to the SU2. So this dimension is simply a Catalan number, 1 over n plus 1 binomial coefficient of n to n. And since I want to model a black hole, I will just take the totally mixed state, meaning that I have no clue what intertwiner state is inside the bulk. So I put the identity matrix on my Hilbert space divided by the dimension. This leads to an entropy, which is simply the log of the dimension, which is in 2n log 2. So that would be if the qubits were not correlated. And then I get a logarithmic correction, which is in -3/2 of log n. So that logarithmic correction tells you that there's some correlations between my qubits on my boundary. So I can look at correlations. So the simplest correlation setting that you can think of is take all my area patches and I cut this thing in two and I look at the correlation between one subset of area of spins and the rest. So I look at the correlation between two k spins and two n minus k spins. It turns out that you can use some trick that Simone said, that you can basically unfold intertwiners, introduce some fiducial spins in the middle, to define a good basis for intertwiners. So I take my two sets of spins and I separate them and I look at the spins which recouples this spin and this spin. So here I call it J. And so this J is going to carry the link, like what's the relation between these two sets of spins. And you can rewrite the dimension of the total Hilbert space as a sum of that intermediate spin and use this decomposition to compute the correlation meant by the mutual information between these two sets. And here I computed between the splitting if I take n spins with n spins. In that case, you compute its number and you look at its asymptotics, and that's exactly the logarithmic correction to the entropy formula. So then once you've got this mutual information, you can move to quantum correlations instead of classical correlation and look at the entanglement. So it's possible to compute all these numbers exactly. But the one which interests me more, it's the case of if I look at the link, the relation between a pair of these qubits and the rest. So if I take two spins 1/2, it can be linked to the rest either by a spin 0 or a spin 1, because two spins 1/2 will recouple to 0 or 1. So if it's a spin 0, it's like the link, the edge was not there. Actually, if you compute the entanglement, it means that this pair is totally disentangled from the rest. In that case, you can consider this pair of qubits or of surfaces as separated. In some sense, you had your big surface and a little ball came out of it. Or you can have an intermediate spin which is 1, in that case, you can compute the entanglement, it is strictly positive. And so the natural thing was to compute the unentangled fraction. So seeing like what's the fraction of my intertwined states which are separated and which are linked together. And then you look at this proportion and it goes as 1/4 when n goes large. So it means that even when the horizon goes super large and I looked at a pair of guys, then there's still a non-zero limit probability that they detach. And so you can turn this probability into some rate of detachment, of evaporation. So, but to do that, you need a time scale. And for a moment, there's no time scale. So let's say the time scale is proportional to the mass because it's this correct unit. And the only mass you have in this problem is the mass of my black hole, which goes as square root of the area, so as square root of n. And in that case, having this non-zero unentangled fraction allows you to recover the Hawking law of evaporation, of course, up to a global factor. So it's an oversimplified model of a black hole, but it still gets the main features of a black hole. So for a moment, I was describing everything if you have like one node inside my bulk. But of course, if I take a region, I would say that you've got many nodes, and actually in the continuum limit, I would have like a super number of nodes. Okay. One can show, if you try to compute some entropy out of that, that in my bulk, if I look at loops inside my bulk, they can carry arbitrary spin. And so it means the spin on these loops can go from 0 to the infinity. So it means if you're trying to count a number of degrees of freedom, you're going to get an infinite bulk entropy. It's not very interesting. But of course, we must remember that for a moment, we just consider kinematical states. So we didn't impose any constraint in the equation of motion in the Einstein equation. So these are not physical states. It's like I'm looking at all possible metrics inside something. I can have wild fluctuation, I can have anything. But if I impose the Einstein equation, meaning that if there's no matter that it's flat, I'm constantly reducing the entropy. So I'm saying that, but we don't know how to solve these Hamiltonian constraints. So it's a nice question to do later and hopefully get a nice answer for the bulk entropy. In the meanwhile, there's two directions of research on this problem. There's looking at something like a typicality of the boundary states. Somehow your boundary states, if you look at that region, the boundary is coupled to the Hilbert space inside. And so, since the bulk Hilbert space can get very large, one can show that it implies that you get some typicality of the state, which is almost thermal on the boundary, to some concentration of measure phenomena. Kind of the same as saying that my boundary is going to be maximally entangled to what was inside, and I've traced out what was inside. And there's a whole idea of focusing on the boundary, so looking at the surface dynamics, which can be very natural from the point of view of holography, meaning that maybe what was in the bulk was not physical, and what's really physical is all the boundary that's living what's all the data that's living on the boundary, from which we would be able later to reconstruct the bulk structure. So if I focus on the boundary geometry, somehow we know that it's determined by the bulk geometry inside, which tells you like how the boundary is. And if you try to project the bulk dynamics onto the surface, then you're going to get some quantum surface dynamics, which will have some dissipation because it interacts with some environment. It's going to have some decoherence. You can add some interactions between the area patches, which can be modeled at leading order as some Bose-Hubbard model. So there's plenty of interesting things that you can do. So now, I've talked about entropy, and I'm going to tell you a bit more about correlations. So for a moment, I looked at only one region of my spin network. When I want to do is look at correlations, so look at two regions and look at the interactions, the correlation between them, or three regions, and so on. So the first setting, it's exactly what I've done. I look at one region, and I look at its a correlation with the rest of my spin network. And so in that case, I want a holographic behavior, which is an area entropy law. So, and this leads to the search for what we call holographic states. So we want to know all spin network states which have a holographic behavior. And this is very similar to identifying states in topological phases in condensed matter. Well, it's exactly the same thing, in fact. Then I can look at two subsystems. So I take two regions, and I'm going to look at the correlation between them. And somehow my initial idea was to try to get a notion of distance from this correlation. And in that case, you naturally go not toward topological phases, but more to like usual statistical physics models that we use in condensed matter, like the Ising model or other models, that at the criticality have a good behavior of algebraic behavior of the correlation in terms of the distance. And then the dream is to go beyond two systems because we like many body interactions. So for example, from three subsystems, trying to get some notion of curvature from the correlations between the multi-body correlations. And it's where plenty of things I've seen already this week can give nice ideas into how to do that. So the goal of that program is to get good states which have a nice large-scale structure, a nice notion of distance which can be used for interpreting my spin network state as some semi-classical manifold. So this is all research in progress. So again, I'm going to oversimplify it to give you an idea of what can be done. So for example, I'm going to fix all spins to 1/2 on my spin network. Easy. I'm going to consider only 4 valence graphs. So basically, the intertwiners can carry either a spin 0, an intertwiner 0, an intertwiner with a spin 1. So basically, now I have a graph with qubits at every node. If I have that, I can easily map it onto some condensed matter model and try to understand what kind of holographic states I can have and what have a good correlation regime I can have. And I'm going to simplify it even more by simply taking a regular lattice. So a graph which is a 2D square lattice, or you can do a 3D diamond crystal, which is, I took that because I wanted 4 valent nodes. So why do I want to take a regular lattice? Is that in the regular lattice, I would have an a priori notion of a distance between sides. So if I have an a priori notion of a distance, I can do all the program of finding holographic states, looking at correlation, and then I can compare my information distance with the actual a priori distance on that lattice and see if I'm going in the right direction or if I'm doing something completely stupid. And so the whole point of that is to be able to compare loop quantum gravity states to states which are used in condensed matter. So for example, if I look at bipartite entanglements, so in the case where I want to recover the area entropy law, so holographic states, the prototype model is the Kitaev toric code model. So to get there, I do a little transform on my graph so that the spins, the qubits, are not at the node but on the edges. And then the model imposes some constraints on every node and every plaquette. So you're going to get a constraint saying that if I flip the four qubits around every node, then it's 1. And if I look at the product of all the spins around a plaquette, it's 1 also. The equivalent, the mapping onto loop quantum gravity, that this is equivalent to the closure constraint, the sum of the vectors being 0. And this is an extra thing, which is a flatness constraint, saying that the holonomy around a loop is trivial. In that case, one can show that all the solution states are condensate of loop operators. So you can compute them. So, well, if you want details later, I can give you details. But basically, on those states, which we know explicitly, we can compute the bipartite correlation entanglement. So you take one region of my lattice, and I look at the entanglement entropy between that region and the rest on that on those solution states. And it turns out that there's a holographic behavior meaning that the entropy of a region, the entanglement entropy of a region with the rest, is proportional to the number of edges on its boundary. Actually, this result can be generalized to work on any lattice, not just square lattice. You can even do it in 3D. And it's even more general than that, but it works for any topological BF theory. So BF theory is a class of topological models, similar to the Kita-F. In which case, the Kita-F model is a special case when it's, the gauge group is Z2. Z2 simply because you've got two states for my qubits. Then you can generalize that to any group, and you can even generalize that to Lie groups. So for example, if you go to BF theory for the SU2 Lie group, you get really full states with all possible spin in loop quantum gravity, and you get the same holographic behavior. And then you can look at correlation between two things, between 2 points or 2 nodes, 2 regions, and the prototype calculation is to use condensed matter model from statistical physics. So for example, build states which have Ising correlations or correlation from other models. So why I take the example of Ising, that it's the simplest and we know it well. In that case, there's a critical regime. In that critical regime, we know correlations between the qubits, the 2 spins at 2 nodes, which goes at 1 over the 4th root of the distance. So in which case, you can invert that relation and get a notion of a distance in terms of a 2-point function. What's an interesting remark for my next slide is that all this, for the Ising model, or for most of the models, you can rewrite these states as loop condensates. Because now, the point of that was to identify classes of good states. So by good states, I remind you that I wanted to have holographic behavior and good decay of the correlation in terms of distances. So there's 2 ways to approach this problem nowadays. Maybe there's more. There's exactly by looking at states which are made of loop condensates. So try to build superpositions of like loops which are small but also large. So basically, having a small loop is going to entangle systems which are on that loop. And so if you want large-scale entanglement, you're going to have to consider also big loops. And in that case, we interact a lot with statistical physics models, which we have a good handle on the long-range structure. And there's lots of work also on Mera-like states, which is multi-scaled entanglement. Renormalization, yes, thanks. Renormalization and that. I always fail. Yeah, and so in that case, the people use tensor network renormalizations and local entangling and little entangling operation to build the model, in which case we can very fine-tune the local structure of the correlations. So in some sense, this can be easier to get the long range, the large scale structure, and this, the local structure. And all these Mera states techniques is also nice because it makes links a lot to quantum computing things, and which offers a nice way to see holography as some quantum error correcting things. It's cool things. It's not my area of expertise, but it's a very nice approach to quantum gravity. Any questions?
Yes. Yes, thank you. You said that you could diagonalize the area operators with this spin network representation.
Mm-hmm.
And so I was wondering, do you have some kind of commutation relations with the area and the volume elements, or is it just commutative?
No, the area is going to commute with volumes.
Okay.
Yeah, no problem. You can diagonalize both of them.
Okay, so
yeah.
Thank you.
On the other hand, if you look at, for example, like fine observables, like on the polyhedron, or at the intertwiner, looking not at the spin, which is carried there, which is the area, but scalar products. Then scalar products are not going to commute with each other. That's why there's some non-commutative structure of space, which you can actually map into some non-commutative geometry model. And what's funny is that the commutator of two scalar products, so if you take three edges and you look at the commutator between this and this, is going to be the volume operator spanned by these three edges. So there's some non-trivial interaction between some observables and the volume.
We start a discussion during the lunch about the time. So, what is now the meaning of the time in quantum relativity?
So here, actually, when we impose the Hamiltonian constraint, it means that the state is invariant under time parameterization. Time parameterization. So you can. It's actually that my state doesn't represent really my physical state, which solves the quantum mechanical equation, doesn't represent the geometry of a 3D slice. It represents the whole trajectory. And so you don't know where you are in the trajectory. So you need to reconstruct time a posteriori afterwards from the evolution. And usually the way we think about it is that we not only we impose an initial slice, an initial state, but we need to put time-like boundaries there and say, like, to impose some constraints saying that, for example, there exists a path in there, like a clock, that's coupled to gravity, but has measured time t. In that case, I look at the coupled system metric coupled to my clock, and in that case, I would have a notion of time. But if I don't have something like that, then basically my state is timeless. And that's the problem of time.
Thus, time and space are emerging.
Yes, it can only be emerging. And yeah, since inside it's all a superpositions of all possible 4D metric, it's even hard to you need to identify like the semi-classical states, boundary states, which pick the 4D metric on a semi-classical, which picks the bulk on a four-dimensional space-time, in which you can then put a coordinate system and say, oh, that's for that most probable space-time there, I have a notion of time. But as soon as it's some quantum superposition of space-time, you lost. Yeah, so you lost.
Okay. So one of the ideas is to use the correlations as distance, and to take the correlations somehow like the length scale at critical critical behavior. So basically, how do you see the normalization framework, in fact, with the different scales in terms of
I mean, the randomization of the Coase graining of this of the spin network state is some open problem.
Yeah.
And the main problem is the absence of scale a priori. So you think, like, for example, I'm going to do a partition of my spin network into like parts of my graph, but then the scale. I mean, how do I know that all these regions have the same scale? Because okay, I can say, oh, it's the number of vertices I've put inside, but this is when I Coase grain, I'm going to change that, and so it's not a good observable. I could say, okay, it's the spins inside that measures the volume and all that. That's going to tell me my scale. But then if I have a superposition of these things, you don't really have a definite answer. You don't have a one scale which is given. So it's kind of strange that if you try to Coase grain a whole class of spin network state with arbitrary spin on a graph, then somehow you have to take different grouping partitions and to look for which partitions allows for a nice semi-classical behavior. And when you optimize, you say, okay, that was that partition that I should use to Coase grain. But this is just words. I'm saying words because nobody had done it, because computationally it's going to be really difficult, so nobody was able to test that idea yet.
my question is also about this way to measure distance by correlation.
Yeah.
So you show the example of the Ising model. Why did you choose the Ising model? Do you have a natural Hamiltonian model? Because the power law will depend on the universality class of your model. So how do you choose this universality class?
I chose the Ising model because it was the simplest model. That was my initial motivation. Then I found a later motivation. Where? Okay. So actually, with this type of correlation, I was not happy because it's not really the right decay for the distance that I would like to get gravity. So I put the Ising model just to illustrate an idea. When I want to find a better model, and I want to do it in something which is going to be 3D, not a 2D thing. In 3D, everything is a bit more complicated and it's more or less all numerics. And do I have the Hamiltonian constraint? Then it is possible to build a Hamiltonian constraint that are satisfied by that state and that characterize it uniquely, basically by saying that the correlation, saying that the volume flips, the volume operators, must be equal to some holonomy between the holonomy operator between the links. But somehow it's basically encoding by hand, saying that the Ising model is coupling nearest neighbors. And actually, this is a limit of this approach of simplifying the model, because this Hamiltonian only works on the class of states that I took, which is putting spin 1/2 everywhere. And so I take it as an interesting guide to try to have inspiration to guess what could be a nice Hamiltonian constraint acting for arbitrary spin networks. But nobody has a good answer yet.